Oh my goodness. Just 1 second, I'm gonna shut the door. Rom, I've got like 13 students. I expected it to be like one. Let me get myself squared away here. Wow, I didn't expect this many students. Can you guys hear me okay? Wait, let me do this here. Can you guys hear me okay? You do, Justin?
Yeah.
Yay. Okay, let me get the review Xerox thing. Yeah, I honestly thought it would just be me and Alexa and nobody else. This is quite a surprise. Here's my chapter 20 test review. Okay. Hey, I might as well start now. Welcome. And now's my time, number one, to answer any questions about chapter 20 and to give you problems like what you'll see on the chapter 20 test. The chapter 20 test will be confined to those types of problems you see on the review Xerox, you know. So are there any particular problems you want me to talk about?
Could you go over number? No, go ahead. Go ahead.
Go ahead, Alexa.
Okay. Number 10, part C in particular.
Number 10, part C. Cool. Here comes number 10. Okay, and I'm gonna have to do it like on a separate sheet of paper, right? I'm gonna draw it. I'm drawing it on a piece of paper right now. Just 1 second. Okay, I have now drawn the circuit, and it's time to do a screen share, which is always kind of a dicey thing with this. Oh, a plugin is required.
Mr. Shayna, I think you're muted. I can't hear you.
Yeah, I can't either.
Yeah, he's muted.
Mute. Okay, am I unmuted now?
Yeah,
I can hear you.
Unbelievable. I got to tell you, man. Okay, well, anyway, I'll stop complaining about stupid technology. So here we go. The equivalent resistance, you know, is the 40 plus the 20 plus the 16 because they're all in series. I know they're all in series because whatever current enters and exits the 40, enters and exits the 20, and also enters and exits the 16. And then those two guys are in parallel with the 50. So 60 plus 16 is 76, and that's in parallel with 50. And so this is going to be 1 over 76 plus 1 over 50 to the -1 power, and that's going to get me, just a second, okay, 76 to the -1 plus 50 to the -1, so that gets me 30.2. So I got 30.2 ohms, yay. And so the current out of the battery, V equals IR. So the current out of the battery is going to be the voltage divided by the resistance. So the voltage is 6 volts. The resistance is 30.2 ohms. So that's going to get me 6 divided by 30. That's going to get me approximately 0.2. Now let's just call it 0.2 amps. Okay, great. So Alexa, that's the current coming out of the battery. And let's go ahead and do the rest of the problem now. This is 0.2 amps coming out of the battery. And do you see that the 50 ohm resistor is in parallel across that 6 volt battery? And so
Yes.
the voltage drop across the 50 ohm resistor has to be 6 volts because one side of the resistor is attached to the positive terminal of the battery via a conductor, and the other side of the resistor is attached to the negative terminal of the battery via a conductor. So since that's 6 volts and that's 50 ohms, I can figure out the current that has to be going through that 50 ohm resistor, and that current is going to be 6 divided by 50, which is 0.12 amps. Well, if I have 0.12 amps passing through the 50 ohm resistor and I've got 0.2 amps going to this node here, then I must have 0.08 amps traveling through that branch. And so that 0.08 ohm amps is going through the 40, the 20, and the 16. And so that's why the answer is about 0.08.
Wait, so how you got the 0.12 was by it was by multiplying 50 times the current, or
Correct. 50
okay.
times the unknown current has to equal 6 volts because it's a 6 volt
Okay.
drop. Yeah, so I ended up doing 50 divided by 6.
Oh, okay.
I'm sorry. 6 divided by 50.
Yeah, I got you.
Yeah. Now the other way to do it, of course, is if there's a 6 volt drop across that 50 ohm resistor, that means that there's also a 6 volt drop across these 3 resistors. So I could have found this current just as easily by going, hey, I've got a 6 volt drop across 76 amps. And so this current would be the 6 volts divided by 76 ohms. I said amps, I meant ohms. 6 volts divided by 76 ohms, and that'll get you your 0.08 amps. So you could have done it that way as well. And that's the beauty about chapter 20 is most of these problems, there's multiple ways to do the problem.
Thank you.
You're welcome. Justin, what problem? Here, I'm going to stop the screen share now. Boop. Okay,
Oh,
Justin.
did you do
what
number 4 for me?
Yes, number 4. You have 3 identical resistors, and they're all 180 ohms. This is number 4 is more of a conceptual problem than a analytical problem. Let me do the screen share again. Okay, great. So, so for part A, what's the maximum current out of the battery? Hey, if I want the maximum current, then I'm going to need the minimum resistance. So, of course, my screen share is frozen. But I'll just tell you, Justin, I'll tell you verbally. Are you okay that to get maximum current, I need minimum resistance? And I'm going to get minimum resistance by having those 3 180s in parallel. And if I have 3 180s in parallel, that's an equivalent resistance of 60 ohms. So the maximum current is going to be 12 volts divided by 60 ohms. I actually did this problem the last time I was doing this with students. So I'm going to actually put my page there, and then 10 seconds later, it'll show up on your screen. There it is. Okay. So Justin, do you see for part A, I've got 3 identical 180s, which is an equivalent resistance of 180 divided by 60. I'm sorry, 180 divided by 3, which is 60. And then I did 12 volts divided by 60 ohms. And that's going to be my current. Whereas for part B, if I want the minimum current, I need the maximum resistance. And the way I'm going to get the maximum resistance is to put those resistors in series. So I've got 3 180s in series, which is 540. And the current is going to be 12 volts divided by 540. And then finally, for part C, what's the minimum power obtained from a circuit? Well, whether you think of power as IV, if you think of power as IV, then you want the minimum current because the voltage is 12 volts. No matter how you orient the resistances, you've got a 12-volt battery. So to get minimum power, you need minimum current, which means you need that 540 ohm equivalent resistance. Or you could think of it in terms of power equals V squared over R, where now, again, your voltage is 12 volts. That's not changing. But to get the minimum power, you need the maximum resistance. So again, you got 540. So any question or issue on that, Justin?
No, that makes sense. Thank you.
Good. Yeah, and what's going to happen tomorrow is, I don't know if I'll ask you for the minimum power or the maximum power, but I'll ask for one of those. And just remember, your maximum power is going to be with maximum current, and your minimum power is with minimum current. Your maximum power ends up being with minimum resistance, and your minimum power is with maximum resistance for a given voltage. Hey, any other questions or issues on this?
You know, for the screen sharing, we could see your credit card in the corner, and I don't know if you want to move it, but yeah.
Really? But you couldn't see the number. All you saw was the last 4 digits, right?
Yeah. So
Cool.
that's good.
Well, then let me just move that a little bit.
I'm sorry, I was just saying, just in case. We're not gonna do anything, I'm sure, but still, either way, it's yours.
Yeah, no, I appreciate that, Sumbal. Yeah.
Okay, thank you.
Yeah, you're welcome. Thanks. Yeah,
I
take
actually just
advantage of the
purchased a
pandemic
private
to make
island.
money. I mean, I don't want you guys to be like Donald Trump.
Can we do number 7?
Robert, it would be my incredible pleasure.
Thank you.
Looking at number 7, the 200-watt bulb is really bright in a parallel circuit. Why is it that the 200-watt bulb is when it's substituted for one of the 60-watt bulbs in the series circuit, the 200-watt bulb doesn't light and the other 2 bulbs are brighter? This is a conceptual problem. The key is a 200-watt bulb has a lower resistance than a 60-watt bulb because the 60-watt bulb and the 200-watt bulb are both connected in parallel. And maybe I can, God forbid, screen share and show it to you real good. Just a second. Okay. All righty. So let me see if it lets me do it. What's that beep? Is that me? Am I beeping? You guys hear a beep?
Yeah.
Was that me? Was I
think
I remember. What's that?
So, sir. I think it's you, sir.
Wow, I don't know what's beeping. Because it sounds almost like a smoke detector.
I think it may be me. Because mine just does that.
Well, I'll have to figure out what's causing that stupid beeping. So, yeah, did it happen just then? Yeah. So Robert, the key is you need to know that the 200-watt, first of all, bulbs are attached in parallel. And in order to have more power, this bulb is going to have less resistance because power is equal to V squared over R. And they both get the same voltage, 120 volts. So whoever's got the higher power is going to have the lower resistance. So let's call this resistance just big R, and let's call this resistance little r. All right? Well,
All right.
so now that we agree that the 200-watt bulb has a smaller resistance, what happens if I put it in series with a bunch of 60-watt bulbs? That is, I've got this 60-watt bulb, this 60-watt bulb, and now I replace a 60-watt bulb with this little teeny resistance of a 200-watt bulb. All right? Well,
Mhm.
do you see that since I reduced the total resistance of this circuit, there's going to be more current coming out of this battery, coming out of this voltage supply than before. When this was a 60-watt bulb, it had a bigger resistance, meaning less current, and so less power being given off by these bulbs. But now that I've replaced the large resistance of a 60-watt bulb with the small resistance of a 200-watt bulb, I'm going to have more current going into this circuit. So these two bulbs, the two remaining 60-watt bulbs, are going to be brighter. But in addition, because all three bulbs are getting the same current, and the resistance of the 200-watt bulb is so teeny tiny, that means that the voltage drop across that little resistance is going to be teeny tiny as well. And so the power dissipated by him is going to be teeny tiny. And so you get a situation that by virtue of having a small resistance, the 200-watt bulb is really bright in a parallel circuit. But by virtue of having a small resistance, this 200-watt bulb is going to have a very small power, which means it won't even light up. It won't light at all in a series circuit. So however you want to explain that will be fine, you know?
Yeah.
But yeah, you're going to have to explain it that way.
Is it
So it's
possible
a pretty,
to
what's that?
explain? Oh, sorry.
Go ahead.
Is it possible to explain number 6 using power?
Yeah, sure. Tell me, how would you explain it?
I was gonna say that the series has more resistance, resulting in less power by V equals V squared over R.
Yeah, beautiful. That's great. That's a great explanation. Yeah,
Okay, cool.
right.
Thank you.
Yeah, that's it. Make sure you mention the formula, power equals V squared over R. And that's the extent of what they would have expected on the AP exam if these problems were on the AP exam, which they're not now. Any other questions or issues?
Could you explain question number 14, please?
Yes, it'd be my pleasure. That's the internal resistance problem. Well, my screen share is still working, so I think I'll just do it here. Okay, so Alexa, when you have a 9-volt battery, here's my 9-volt battery, there's positive and negative. A 9-volt battery actually consists of both the voltage supply and the internal resistance. Because when charge is passing through a battery, it still has to fight its way through the battery. It has to go from the anode to the cathode or vice versa, depending on how you look at it. But regardless, there's an internal resistance to a battery, but it's not an internal resistor that you can like chop open a battery and remove it. The internal resistance is innate or inherent to the battery. So inside this dotted rectangle, this is actually the battery right there. And the battery consists of both the voltage supply, which people call the EMF, and the internal resistance. Okay, so we're going to put a 6 ohm resistor across the terminals of my battery. And they tell me that the terminal voltage ends up being 7 volts. That is, if I put a voltmeter onto the 2 terminals of my battery, my 9-volt battery isn't a 9-volt battery anymore. It's a 7-volt battery. And you need to get 2 things. You need to get the voltage drop across R sub I, and you need to get the current through R sub I. Well, the voltage drop across R sub I is easy because the voltage of my 9-volt battery, that point right there is 9 volts, but they tell me the terminal voltage is 7 volts. So my voltage drop across this R sub I must be 2 volts, 9 minus 7. So the voltage across the internal resistance is 2 volts. to get the current through the internal resistance, I'm going to actually end up getting the current through that 6 ohm resistor, because it's a 7 volt drop in 6 ohms. So the current is going to be 7 volts divided by 6 ohms. So now that I've got the voltage drop across the internal resistance and I have the current, which is 7/6 of an amp, that current, which is going to be the current going through this entire circuit, so that internal resistance has a current of 7/6 of an amp, I can go ahead and do 2 volts equals the 7/6 amps multiplied by the internal resistance. And so I get an internal resistance of 12/7 of an ohm, which ends up being 1.71 ohms. So Alexa, is that process, are you okay with that process?
Wait, so so you got the 12/7? Is that 12/7? Is that what I'm?
Yeah, what I did was, since I have 2 volts, V equals IR, since I have 2 equals 7/6 times R, I multiplied both sides of the equation by 6/7.
Okay.
To solve for R sub I.
Okay. All right, that makes sense.
Good. Hey, any other questions or issues?
How would you do number 11?
Number 11, for the circuit shown on
Yeah.
problem 10, redraw the circuit to show where the ammeter and ohmmeter goes. Okay, here's problem number 10. And you need to know that ammeters have to be in series and voltmeters have to be in parallel. So if I want to put an ammeter to measure, I would have to do this. My ammeter, let me put it in red. Okay, well, too late now, it's black. But anyway, do you see that ammeter there? The ammeter would have to be in series. Like the way I would do it is, if this is the 20 ohm resistor, then I would have to make a cut in the wire and then put my ammeter there and then go ahead and resume the circuit, and then here's my 16 ohm. You see, but your ammeter has to be in series. And I want to remind you that the ideal resistance of an ammeter equals 0.
Yeah, okay.
Similarly, if I want to measure the voltage drop across that 20 ohm, then I need to put my voltmeter in parallel across the 20 ohm. That is, I need the red lead to be on one side of the 20 ohm and the black lead to be on the other side of the 20 ohm. That's where you would put your voltmeter to measure the voltage drop. And I want to remind you that the ideal resistance of a voltmeter is infinity.
Yeah, I would have done that wrong then.
And that's it. That's the extent. That's all I would need to see, that the ammeter goes in series and the voltmeter goes in parallel to get a right answer.
Yeah, I would have done that wrong. I would have put the voltmeter with the 50, not the 20.
Gotcha.
Yeah, that would have been
bad. Oh, there we go. Okay. Hey, any other questions or issues?
Can you go over number 19?
Yes. Is that you, Cameron? Who's that?
Yeah.
Cameron? Okay.
Yeah.
19. First of all, the first thing you should know about number 19 is it's not going to be on the exam. I'm not going to put any review problems, even though 19 is a beautiful problem. I don't know, maybe I'll make it an extra credit. Probably not. Yeah, I'm not going to put it on. So Cameron, I'm just going to answer the question verbally, just between you and me.
Okay.
Part A, normal force does no work because the normal force is perpendicular to the velocity.
Okay.
The same reason that a ball on the end of a string, the string doesn't do any work when the ball's spinning in a circle. So that's part A. Part B, the maximum displacement of the spring as it stops the box. You're going to have to do conservation of mechanical energy. You're going to have to let the initial mgh equal the final 1/2 kx squared. So that's how you do part B. Just do mgh equals 1/2 kx squared, and that would get you the maximum displacement of the spring. Before I go on, does that make sense?
Yeah.
Okay, then looking at part C, now we remove the spring and replace it with a blob. And remember, this ramp is frictionless. So now in order to get the speed of the block right before it hits the blob, you're going to have to do conservation of energy again, but now mgh is going to equal 1/2 mv squared. So you would use conservation of mechanical energy to get the speed of the block right before it hits the blob. And then to get the speed of the block and the blob after they collide, you would use conservation of momentum.
Okay.
That is the mass of the block times its velocity right before the collision equals the combined mass of the block and the blob times the velocity of the blob after the collision. So that will get you the speed of the blob after the collision, and then you would use kinematics to find how far it was from the table when it landed, and you would do the y direction first. Do the y direction to find the time, and then do x equals vt to find the distance.
Okay, thank you.
You're welcome. So it's a pretty nice problem. Anything else on any of this review Xerox stuff?
Number 18.
Number 18? What's number 18? Oh, my Kirchhoff's rule problem. Okay, and who asked for that? Is that you, Robert?
Ryan.
No.
Me.
Ryan Mallon?
Yes.
Okay, so looking at 18, I gave you in the lesson and on that worksheet I gave you, it's essentially a 3-step process for doing Kirchhoff's laws. Step 1, you have to define the direction of all the currents in your branches. And so I just randomly defined I1 is going to the right, I2 is going down, and I3 is going to the right as well. Once you've defined the direction of your currents, you've got to label what the direction of the voltage drops across all your resistors are. So since I1 is entering the left side and exiting the right side of the 30 ohm, your voltage drop is going to be from there to there, because your current will have more energy as it enters the resistor versus as it exits the resistor. And so I'm going to call that voltage drop IR, so I1 times the resistance 30 ohms. Similarly, your voltage drop across the 10 ohm resistor is oriented like that, and the voltage drop is 10 I2. And then finally, the voltage drop across the 50 ohm resistor is oriented like this, plus and minus, and that's 50 I3. Once you've labeled your resistances, now you just choose a loop and start at a point and go clockwise or counterclockwise, and just go around and have an equation where all your voltage rises are on the left side of the equation and all your voltage drops are on the right side. So looking at this leftmost loop, if I start at A, I have a voltage rise of 10 volts because I'm going from negative to positive. So the voltage rise of 10 volts goes on the left side of the equation. Then I encounter, as I go around this loop clockwise, I encounter a voltage drop of 30 times I1. That goes on the right side of the equation, 30 I1. Then I encounter another voltage drop, 10 I2. So that goes on the right side of the equation. And then finally, I encounter this battery, and this is also a voltage drop going from positive to negative. So that 30 ohm goes on the right side. Similarly, looking at the right-hand loop, if I start at point B and go around clockwise, I've got a voltage rise of 30 volts. I've got a voltage rise of 10 times I2. Then I've got a voltage drop of 50 I3 and a voltage drop of 20 volts, and that's going to be my equation. And then finally, I get Kirchhoff's current rule, Malin, and I'm just blabbing away, but ask me any questions if you have any. I look at a node and I say, okay, all the currents going into the node go on the left side of the equation, all the currents coming out of the node go on the right side. So I've got I1 equaling I2 plus I3. And that's all I'm going to ask. I'm not going to ask you to solve for I. You're not going to have to solve 3 equations and 3 unknowns. All I need are the equations themselves.
Okay, yeah, because that's where I got confused, because the question was like specify the like current and direction. And I was like, I can't figure that out.
Yeah, if we were not in the middle of a pandemic, then I would offer extra credit for finding the current. But right now, things the way they are, I just want the equations, which actually on the AP exam, that's all they want to. On the AP exam, they don't make you solve for any of the currents. They just ask for the equations themselves.
Okay, thank you.
Wait, so to clarify, if there's a voltage drop, then it'd be like on the right side of the equation, and if it's a rise, it'd be on the left, or
Absolutely. Yeah.
okay.
Because what we're doing is like conservation of energy, and essentially the sum of the energies your charge gains has to be equal to the sum of the energies that the charge loses, so that the total change in energy as the charge goes from point A all the way around to point A, you know, that the sum of those energies has to be zero. The charge can't gain or lose energy. So, hey, any other questions or issues?
For 19C, why can't you just do mgh is equal to the 1/2 mv squared? Why do you have to like find the conservation of momentum?
Oh, I just did it because it was easier. But you could also do, you could find the acceleration of the block down the ramp and use kinematics to get what its speed is right before it hits the blob. Did you do it that way?
No. Oh, it's because it's accelerating. I see.
So you good on that?
Yeah. Thank you.
You're welcome. Yeah, and it's interesting because the fact of the matter is you could choose any angle. It does, if you're 2.5 meters high and it's frictionless, you could choose any angle you want for that inclined plane, and you would get the same final speed using, you know, acceleration down the ramp and then kinematics. So that's why I didn't get around to labeling the angle, because the fact is it doesn't matter. Hey, any other questions or issues?
Can you go for number 8?
Number 8, for following home circuit, draw where the fuse would go. Yeah. Number 8, all I want you to know is the way a fuse works is it has to be in series with everything else. So that when the fuse breaks, all the fuse is a switch. And if you pull too much current, the fuse essentially is a switch that turns off. The switch goes from making a connection or making a circuit to not making the circuit. And then once the switch turns off, no current can get past this point. And so all of the items that are trying to receive current, they don't receive current anymore. So that's all. I just want to make sure you know that a fuse has to be in series. And so you could put your fuse there or there. Either of those two places would be fine, on the top or on the bottom, as long as when it opens up, no current can any longer flow to your circuit.
Thanks.
You're welcome.
Mr. Shana,
Yes.
for number 3, did we need the information like that it was 4 meters, that the copper wire was 4 meters, or could we have done it without knowing that?
How interesting. Yeah, yeah. I don't know why I put the 4 meters there. I guess just to fake you out or something. You're right. It didn't matter. You don't need the 4 meters.
Gotcha.
And then it's 9/36 because the radius is squared, right?
Correct. Yes.
Okay.
If you multiply the radius by 6 or the diameter by 6, then you're multiplying the cross-sectional area by 36.
So, Mr. Shana,
Mm-hmm.
on number 16, just to make sure, the reason that it's 3/4 is because it's passing through 3 resistors out of 4, right?
Correct. Yeah. And for a voltage divider, the voltage drop from A to B comprises the voltage drops of the 3 resistors. Yeah, you might think of it as you've got a voltage divider where I've got a resistance of R and then a total resistance of 3R. So in a series circuit, because this resistance is 3 times that resistance, you know, the resistances of 3R is 3 times that of R, that means the voltage drop is going to have to be 3 times as much. And so that means that he gets 3/4 of the voltage and the other resistor gets only 1/4 of the voltage. Yeah. Did I say the answer? Yeah, 3/4 V. Yeah. And the same thing happens with the current divider, only it's the opposite. Because this resistance is only 1/3 of that resistance, this resistance has to get 3 times the current. And so this current is going to be 1/4 I, and this current, oh, my finger froze, and this current's going to be 3/4 I. He has 1/3, he has 1/3 of the resistance. He needs to get 3 times the current, and the only way that happens is if he gets 3/4 of the current, and the other 3 resistors get 1/4 of the current. Any other questions or issues?
When will you be posting this this recording of this meeting?
Oh,
Will
I
be
can
posting
post it almost right when we're done. It takes about 10 or 15 minutes to, to compile it and then upload it.
Oh,
Mr. Shana, can you do number 3?
Number 3?
Yeah.
Sure. I don't think that was me. Okay, so Nick, you see number 3?
Yeah.
Red? Okay. My initial resistance, my 6 ohms, is equal to rho times L over A. But now I'm going to get a new resistance where I have 9 times the length and 6 times the diameter, which means 6 times the radius. Are you okay that 6 times the radius means 36 times the cross-sectional area?
Yeah.
Because the area is pi r squared. And so you'll notice I put 9L instead of L, and I put 36A instead of A, which means I've got 1/4 times rho times L over A. And rho times L over A, we already decided was 6 ohms. That's why it ends up being 1/4 times 6 ohms.
Oh, okay. Thank you.
You're welcome. And this is remember those problems we used to do with gravity, where I'd say you go to another planet that has 3 times Earth's mass, but 4 times Earth's radius? This is kind of the same way. You're doing these problems the very same way. Anything else?
can you do number 2?
Sure. For a 3-volt battery, how much work is 1.5 coulombs of charge exiting the positive terminal able to do? This is a problem where I'm just making sure that you're aware that if I have a 3-volt battery, that's the same as the battery. Each coulomb of charge has the capacity to do 3 joules of work. So a 3-volt battery is a 3 joules per coulomb battery. And now if I'm going to have 1.5 coulombs of charge exiting the terminal, then if I multiply my voltage by my amount of charge, that'll get me my joules, because the voltage is joules per coulomb. And then if I multiply by the number of coulombs, that's how much joules I have. So to put this in a more equation-y way, what we have is work equals Q times V. That's kind of like the big formula. Your work or your energy is always going to be the amount of charge multiplied by the voltage. Because voltage is joules per coulomb, and so if you multiply by coulombs, you got joules. Are you good on that, Rosary?
Yeah, thank you.
You're welcome. Yeah, and that's it. The whole point of that problem is just to make sure you know what it means for voltage to be actually the same as joules per coulomb. Any other questions or issues on any of this wonderful stuff?
Do we have to do the extra credit part of number 41? So like, would that be number 20?
The extra credit part of number 41. Are you talking, wait, you talking about this?
Yeah, would that be like, yes.
Oh,
would that be
yeah.
number 20 or?
Yeah, I'm not sure, because you're only going to have 45 minutes. And so I have to decide what do I take off of exams? And the first thing I tend to take off are the extra credits, because the extra credits tend to be really time consuming. You know, like I don't want you spending 10 minutes on the extra credit problem when you should be spending those 10 minutes doing the other problems. So Robert, if I did give you an extra credit, it would probably look almost exactly like this, where you would have to get the equivalent resistance, the current out of the battery, and then figure out what they want, you know? So what are you asking about that extra credit?
I mainly was this, if I was asking if that would be a part of the homework, like
You mean
to
part of the
do that
exam?
one.
Yeah.
Yeah.
Yeah. I mean, it's fun to do, especially if I gave this as an extra credit, you know, definitely finding part A, the current out of the battery, is totally doable. That's something you could do pretty darn quick. To answer the other questions may take a little bit more work, but you could definitely, here's the equivalent resistance right there, correct? 10 plus 20 plus 30. 10 plus 20 plus 30, and that's 60, and that's in parallel with the 40. And then that answer is in series with the 50 and the 60. And then that answer is in parallel with the 70. And then that answer is going to be in series with the 80 and the 90. So you end up getting something that looks like that. That's my equivalent resistance. Then you take 12 volts and divide by that, and there's your current out of the battery. And that's like, you know, 1 or 2 extra credit points right there that you could get pretty quickly, you know?
Yeah.
But just to tell you the rest of it, I would refer to the drawing. Once you find the current out of the battery, you can find the voltage drop across the 80 ohm by doing current times 80. You can find that very same current times the 90 to get the voltage drop across the 90, and then you could figure out what the voltage drop from A to B is. Because you'll start with what is that, 12 volts, and you'll lose whatever voltage you lose here, you know, goes to part A, and whatever voltage you gain here, because remember this is 0 volts. So when you do current times 90, that's going to give you a voltage at B. Then you do the voltage at A minus the voltage at B, and that's your answer to part B. And then to get the current through the 20, it's going to be a lot more work.
Okay.
Yeah, thanks for asking. Hey, any other questions or issues? Well, then let me ask this. Oh, go ahead. Hearing something. Would you? Uh-oh, Nick. Wait, who is that? Who was just talking? It said Nick. Is my thing messing up?
He can give you a message since his mic isn't working, I think.
Oh, his mic was working a moment ago. I wonder if it's not somebody's internet. Yeah, where's those messages? I think, do I even allow that? Where is that? I'm not seeing.
No, you can't. I don't think we can do chats.
Yeah, I may have disabled the chat. Or I probably didn't disable the chat. It got disabled for me by administration because they don't want you guys chatting with each other and saying bad things or something. Let me ask this: do you want me to make up a problem and have you try one?
Why not?
Okay. Hey, you know, and if that's something you want to do, then stick around. If not, then don't stick around. Alexa, I'm going to let you choose. Which problem would you like me to give you a problem like?
Okay, something like problem number 18.
Problem number 18. All right. Let me look at. Oh yeah, the Kirchhoff's laws. Yeah. 18. Okay. Here we go. Let me draw it and then I'll screen share it. We're doing a problem like 18. Let me see if I can make it more interesting. Okay, so I'll call this 20 ohms. I'll call this 30 ohms. I'll call this 10 volts. And I'll call this, let's call this 15 volts. All righty. Screen share. Um, so here's the equation. And I am going to define I1 as going this way. I'm going to define I2 as going up. And I'm going to define I3 as going this way. And all I want you to get me are two Kirchhoff loop rule equations and then one Kirchhoff's current rule equation. So good luck. To get me those three equations using those currents in the direction that I put them. Good luck. And that's what I'm going to do. I'm actually going to choose the current and the direction. Heck.
It's like really out of focus.
And if anyone doesn't know where to start, I will tell you. Yeah, that must be me. I'm going to mute myself and see if that noise goes away. I heard the noise even when I was muted. That's interesting. Keep working, but by now you should have determined that the voltage drop across this resistor we're going to call 20I1, and the positive and negative are as shown. And the voltage drop across this 30 ohm resistor is going to be 30 times I2, and the voltage drop is as shown, the positive on the bottom and the negative on the top. Once you got that, then you can just get your rules. Okay. Hey, let me know when you're done. Here, let me, I don't know if I can see all of you at once when I'm screen sharing. It's so funny. I'd like everyone to put your hand up when you're done, do that reaction thing. Put your hand up or a thumbs up when you're done. Stephanie, yay. Kyler's here. Wait, I've got 2 Kylers. Wait, I can't have 2 Kylers, can I?
Yes, I have a computer and a phone, please.
Hey, what? Wait, what did you say, Kyler? You've got a computer, what?
I use my phone to talk and the computer to like see a big screen. So.
Oh, how interesting. How cool.
Yes. Can I do that, please?
Yeah, sure. You
Cool,
do whatever the heck you want. That's so cool. Yuning has got done. Yay. Four participants raised hands. Rosary's done. Yay. She clapped. I'll tell you, man. The only way we're going to get through COVID, you know, the only way we get through the, yay, 5 participants. The only way we're going to get through coronavirus is infinite testing. Could you imagine at Etowanda High School if we had a 5-minute test where like once a week you came to school and they just did a finger prick and then they could tell you if you have it or not. And then if you have it, you stay home for 14 days. That'd be amazing. We could get rid of the virus. I mean, we could conquer this. And we don't have to stay home. Okay, kids. Well, I'm going to assume enough of you are done. So let's go for it. Looking at this leftmost loop, I've got a 10-volt voltage rise as I walk clockwise. And then I've got a 20 times I1 voltage drop. Then as I continue walking clockwise around the loop, I've got a 30 times I2 voltage rise because that's negative and that's positive. So there's my first equation, 10 plus 30 times I2 equals 20 times I1. Looking at the right-hand loop, if I start from this point here, I've got a voltage drop, which is 30 times I2. And then as I continue on, I've got a voltage rise of 15 volts. So there's my second equation. I could also get a third equation by considering the whole outer loop, where I'd have 10 on the left side and 15 on the left side. So I'd have 10 plus 15 equals 20 times I1. I could get that by considering the entire loop. And then finally, I'd have I1 plus I2 equals I3. Hey, any questions or issues on that?
Could you explain how you got the second equation for the Kirchhoff's loop rule?
Sure, it'd be my pleasure. I'm starting from point B. Your little walking man is going to walk clockwise around this loop. And whenever it encounters a voltage drop, that's going to go on the right side of the equation. And whenever he encounters a voltage rise, that's going to go on the left side of the equation. So as he starts from B and walks, he encounters a voltage drop of 30 times I2. So that goes on the right side of the equation. Then as he continues walking clockwise, he encounters a voltage rise of 15 volts. And so that goes on the left side of the equation.
Oh, okay, that makes sense.
And interestingly, this is an easy enough problem that you could actually figure out, you know, what the answer is. Any other questions on this Kirchhoff's loop and current rule? Or I guess they call it junction rule, don't they? Kirchhoff's junction rule. Any question?
So is it always just I1 plus I2 equals I3?
Well, no. In this case, I mean, if I had decided to draw the I2 going in the opposite direction, then it would have been I1 equals I2 plus I3.
Okay, so how did you get it to be like I1 plus I2 equals I3?
Because randomly, I decided to draw the direction of I2 as entering the node. And so these two currents entering the node has to equal the current exiting the node. It's like two rivers, two tributaries coming together to form one mighty river. And so the amount of current in this river plus the amount of current in that river has to equal the total amount of current after the two tributaries join together.
Wait, Mr. Shina,
Yeah, okay, yeah.
Yes.
how is it possible that, like, from the point B to the junction point, how can the current flow that way? Isn't that, like, against how it's supposed to flow?
I don't know. I mean, the way you would figure that out is if you get a negative answer, you know?
Okay,
But-
so
but
what
in
if
this-
what if you made it go downwards instead of
Yeah,
upward?
if I made it go downward, then this second equation would be 15 volts plus 30 I2 equals 0. And so I'd get I2 being negative 1/2 of an amp. And at that point, since I got negative 1/2 of an amp, I would know that I drew my direction wrong.
Oh, okay.
But I can't help myself. I just randomly tend to always draw my currents in the correct direction. Just because I
Okay.
can look at a circuit and figure out which way the currents are going to go. But yeah, so on the test tomorrow, maybe I will draw the current in the wrong direction. It won't matter because you're not going to actually get the current. It's just going to be enough for you to write down the formulas, the equations rather. Any other issues on this? Okay, then, hey, I'm going to do one more problem, and then I'm going to have to call it quits because my daughter has to get the laptop because she has a Zoom appointment with one of her little friends at 5 o'clock. They do art together. So here we go. Here, I'm going to say that this is a 15 volt battery, and I've got two resistors here. This is 20 ohms, and this is 30 ohms, and this is point A, and this is point B. And I want the voltage drop from point A to point B. And then I'm going to have this. This is 15 amps. And then this current is going to split up into 20 ohms and 30 ohms. And I want the current I. So good luck, you guys. Find me the voltage drop from A to B and find me the current through the 30 ohm. My stupid thing. There we go. I'll give you one more minute and then that's it. I'll declare us done. Okay, well, hey, time's up. Hopefully you got that. This is 30 out of a total of 50, so he's going to get 3/5 of the voltage. 3/5 times 15 volts or 6 volts. And here, since he's got 3/5 of the resistance, but he's got more resistance, he's going to get less current. So it ends up being actually 2/5 of the 15 amps. So it ends up being 4 amps. So those are your two answers, 6 volts and 4 amps. Any questions or issues on either of those?
Did you write 18 volts or 15 volts in that?
It should be 15. So this is 15.
Oh.
Yeah, because this is 15. I made, the voltage and the amps 15 just for the heck of it.
2/5 times 15 got me 6.
Yeah, okay. Yeah, let's try that again. 3/5 times 15 is 9, and 2/5
Yeah,
times
okay.
15 is 6.
Okay, that makes sense.
Yeah, other than the fact that I can't do that math. See, I needed Clea. I need my daughter to help me on that because she's actually learning to do that right now. I could have really used her help. My bad.
Can on the second part,
Yes.
is there a way to do it without like the 2/5 thing? Like, can you do it like normally?
How do you mean do it normally?
Isn't there like don't you have to do like equivalent resistance or something, or am I?
Oh, yeah. We could do that. Okay, the equivalent resistance between a 30 and a, oh, wait, whoops, clear. Here, I'm going to do it on my calculator. 30 plus 20 to the -1 is 12. So Kyler, if you want to do it the regular way, then you've got an equivalent resistance of 12 ohms, right? A 30 and a 20 in parallel is 12 ohms. And if I've got 15 amps going through 12 ohm resistance, then, whoops, 12 times 15. Why am I using my calculator? I know it's 180. So I know that this voltage drop is 180 volts, right? So since I've got a 180 volt drop across the equivalent parallel resistance, that means that I'm going to have a 180 volt drop across each of those individual resistors. So 180 divided by 20 gets you 9 amps, and 180 divided by 30 gets you 6 amps. So Kyler, you could do it that way and not even use a current divider.
Okay. How'd you get what 12 for the equivalent resistance again? Sorry.
I got 12 because 1 over 20 plus 1 over 30 to the -1 power is equal to 12 ohms.
Oh, okay.
That's
Thanks.
the formula for equivalent parallel resistance. Yeah, I'm showing you current divider as a shortcut, but if you don't, it's okay if you don't want to use that shortcut. You can actually do it this way, the hard way, and still be fine. Okay, anything else?
What exactly makes it 2/5?
Because since the current through the 30 ohm has to be 50%, well, the current, since the 20 ohm has 2/3 of the resistance of the 30 ohm, then the 30 ohm has to get 2/3 of the current of the 20 ohm. And so the way you can ensure that the 30 ohm gets 2/3 of the current of the 20 is to actually add the resistors together, which is 20 plus 30, which makes 50. And then the current the 30 is going to get is 20 out of the total 50 times the 15. So you're adding up the two resistors, and then however much resistance the other branch has, that's what goes on top, and that tells you what share of the 15 amps you're going to get. But you're having to make sure that since he has 50% more resistance than this guy has to get 50% more current than this guy. But the way it works out mathematically, let me just draw this really quick, is if this is here, if this is some current I, and this is R1 and this is R2, and let's say you want the current I1 that's passing through R1, it turns out that I1 is R2 over R1 plus R2 times I. That is, it looks like the voltage divider, only you use the other resistor. That's just the way it works out mathematically. And at this point, kids, I'm gonna have to end the lesson because my daughter is waiting for the computer.
Oh, wait,
So-
wait, hey, one last thing. What time is the test tomorrow?
Oh, just at our normal time, 12:30.
Oh, okay.
Yeah. What's that, Rob?
How many problems is it, and how much time do we have?
Nah, I'm good. Thanks, though, Rom. Let me stop the screen share. You guys will have 45 minutes, and it'll start at 12:30. And then after 45 minutes, then you're going to have to upload it to the Google Classroom.
Is it like on Google Classroom or Zoom, or where do we go?
Oh, you mean to find the actual test itself?
Yeah.
I'm going to actually have it as an attachment on School Loop, Loop Mail, and I'll also have it as an attachment in your Google Classroom. So,
Okay.
you go to either of those two sources, you will find the test.
And do we have to do a video call?
Yes.
Or-
Yeah. I do want to see your video. That's the only way I can ensure that, well, that's what I suspect the AP exam people are going to require of you, so that you can't cheat during the AP exam. They're probably going to require that you be making a video connection while you're doing the exam.
So is that gonna be on Zoom?
What's that?
Is that going to be on Zoom or?
Yeah. It'll be on Zoom.
Okay.
Yeah, so we're essentially just going to get together at Zoom, and I'll be looking at you as you are now, except I'll be seeing all of your video, unlike now where no one is showing their video. But tomorrow I'll be looking at all your videos, all 28 of you, or no, I guess it's going to be all of you at the same time. So all like 70 something of you, and all I'm doing is just making sure you're not looking at other sources to try to find answers. But again, the biggest reason I'm doing it this way is not because I have this fear or paranoia that you're all cheating. I'm doing this just because I suspect this is what the AP exam people are going to do. So I want you to kind of be aware, be used to it.
Okay, thank you.
Yeah, you're welcome. Yeah, you're welcome. Okay, I'm going to end the meeting. So goodbye, everybody.
Bye.
End meeting for all.